Hello everybody, um, welcome to another Gregorius Maths video. I'm currently filming in Spain, hence the different setup, but that won't stop me from producing Theorem of the Week, let it never be said that Gregorius Maths is an inconsistent uploader. So, here we go. Today I'm going to be talking about a nice little theorem about cohomology operations. And a way to classify them. You see what I mean? Um, so first, we should probably talk about what is a cohomology operation. So firstly, one should note that cohomology in general is a bit better than homology because cohomology comes with a ring structure as well, which is additional algebraic structure which we can use to figure out geometric problems. And so this ring structure is given by the cup product. But we can get even more structure by not only talking about the cup product, but an infinite family of operations, of which the cup product is just one example. And these are cohomology operations. For example, the Steenrod squares, you might have heard of those. Those can be used to prove various things, like the Hopf invariant 1 problem. So these things are definitely useful. It's always nice to have extra structure to work with. So yeah, that's kind of the motivation for this. So what it actually is, a cohomology operation of type pi n g m, is a natural transformation of functors for some space x. We'll have a natural transformation theta x, which goes from the nth cohomology of x with coefficients in pi to the mth cohomology of x with coefficients in g. And so if we want to be more explicit about this, for any f from x to y, then this diagram commutes here. So that is what a cohomology operation is. Now we go on to what the actual theorem of the week is. So the theorem is, and I forgot to define what this is. All this notation here is the set of all cohomology operations of this type. And the set of all cohomology operations of this type is in direct correspondence with homotopy classes of maps between the Eilenberg-MacLane space of pi n and the Eilenberg-MacLane space Gm. So what that means is this space has one non-trivial, I don't know if you can see my mouse, the first space, so this pi n, has one non-trivial homotopy group, and that is pi n of this space is equal to the group pi. And similarly, this second space here has one non-trivial homotopy group, and it is the mth cohomology of this space gives us G. So that's the definition of these Eilenberg-MacLane spaces. And a corollary of this theorem is that the set of all cohomology operations is in direct correspondence with the mth cohomology of our Eilenberg-MacLane space with coefficients in G. And that follows from a nice theorem about singular cohomology, which I would write down, but I don't have an epic pen. So hopefully you know the theorem. If not, I'll link it down below somewhere. So this is direct corollary. Now, okay, thankfully for us, the proof is not actually that difficult. We can rely on a theorem which I've proved earlier in this series. That is the Yoneda lemma. Now, this is a slightly more specific version of the Yoneda lemma. The Yoneda lemma that I proved in Theorem of the Week a while ago is the general categorical statement, but this is a special case. So if we have this functor k such that k of x is the set of all, here I mean based maps, by the way, Here K of X is the set of all homotopy classes of base maps from X to some space Z, where Z is fixed. If we have this functor here, and another contravariant functor K prime, which also maps from the homotopy category base CW complexes to sets, then what do we have? Well, we have that the set of all natural transformations between K and K prime is isomorphic to, or in correspondence with is probably more precise, K prime of Z. And so if we apply this to when K prime is also a representable functor, then what do we have? Well, we have set of all natural transformations between K of dash and K prime of dash is in correspondence with K prime of Z. But in this case, K prime of Z is just the set of all homotopy classes of maps between a base, well, I mean based whenever I say homotopy class of maps, set of all based homotopy classes of maps between Z and Z prime. And so this will be very useful because now, what do we have? Well, by definition, the set of all homotopy classes of maps, the set of all these cohomology operations of this type is equal to the set of all natural transformations between these two functors. I forgot a bracket. But that is that's isomorphic to the set of all natural transformations between these two functors here, because it's a classic theorem that the singular cohomology is in direct correspondence with these homotopy classes, homotopy classes and maps. But by the version of the Yoneda lemma which we stated above, this is precisely isomorphic to the set of all homotopy classes of maps between these two Eilenberg-MacLane spaces. And so, yeah, that's the proof. I mean, maybe not the most exciting theorem of the week, I'll grant you that. I more kind of wanted an excuse to talk about cohomology operations. But yeah, that's that. I feel like I said a bunch of stuff. Probably would have been a lot easier if I had a pen. But nonetheless, we are working with a slightly worse setup, so we move. Yeah, that's theorem of the week. And of course, because of this theorem, the study of the cohomology of these Eilenberg-MacLane spaces is important because, I mean, it's in direct relation to these cohomology operations. And yeah, that's all I wanted to say for today. I'm not going to waste any more of your time. Goodbye.